Okay, so on to section 8.3, and in 8.3, the text is discussing how you can use first-order logic and demonstrates it basically through examples. Okay, and so the section starts off by talking about examples using some simple domains, and in knowledge representation, when you have a domain, what you're doing is you're just talking about some part of the world for which you want to have some discussion about knowledge, or you want to express some knowledge. And so we have to start off by talking about this tell-ask interface. Okay, so if you have some kind of a knowledge base that has been implemented, you have to have some way to be able to express some facts, right? You have to be able to tell the knowledge base some sentences, something that it's supposed to know, and you have to be able to, ask the knowledge base questions, right? So, your tell, your ask could take the form of, maybe some methods in Java or C++ that serve as kind of like a front end for a knowledge base, or if you have, a logic programming language like Prolog, well, then the tell takes the form of statements that you write in the Prolog program, and then queries, or the asks take the form of queries that you could make of the knowledge base in the Prolog program, okay, through the interpreter. Okay, so I'm going to talk about what this is and kind of how it works. So what you have with knowledge bases is you have to have the ability to interact with the knowledge base using what's called a tell in the textbook, and these are often referred to as assertions, right? So you're making some assertions of facts, right? So you're telling the knowledge base, hey, these are some things that you need to know. Okay, so tell, right? So you might need to assert that John is a king, Richard is a person, all kings are persons. Basically, these are just things that you're letting the knowledge base know, okay, through an interface that the textbook refers to as tell. So when you see this here, you're basically just saying, hey, look, I'm telling the knowledge base that I've got a king who is John, okay? I'm doing a tell to the knowledge base saying, look, Richard is a person, okay? And I'm telling the knowledge base that for all objects within the domain, if it's a king, then that implies that that thing is a person, okay? So this is kind of like, if you have pseudocode algorithms, you'd have to be translating the pseudocode into the language of your choice that you're trying to implement that algorithm into. Well, it's kind of a similar thing here. When you're dealing with some kind of a knowledge base, and in our case, we'll have assignments in Prolog, you have to be able to make those assertions. So you're translating what the text is telling us here in theory into the language of your choice, right? Or into the knowledge base implementation of your choice, okay? Now, we need to be able to ask questions of our knowledge base, and the textbook uses this generic term ask. So we're asking the knowledge base, if you know about King John, and that's going to return true. So these questions are often referred to as queries or goals, okay? And the more you dig into Prolog, you're going to start seeing this language more and more and more and more. Okay, so queries are queries that are logically entailed by the knowledge base should be answered in the affirmative, right? So if you ask the knowledge base if John's a person, then it should return true as well. All right, so how about asking quantified queries? All right, so we might ask the knowledge base, do you know if there is a person in your knowledge base? So, this is kind of maybe not the most useful type of question. So, this is going to be kind of crude. It'd be like asking for the time, and the answer is true, right? So, if you're trying to ask, well, can you tell me about who all the people are, if there is a person, or what if you know of a person, then we are going to need something a little bit more maybe useful, or maybe something that's going to be a little bit more elegant or more wieldy. So we might want to ask, be able to ask about what makes something true. So we can have another type of query that gives us a stream of answers, right? And again, as you're playing with Prolog, you're going to see this kind of behavior implemented. So we might ask the knowledge base, tell me about all of the persons that you know about, right? So we can get a stream of answers that might look like something like this, where we have one value for x is John. Okay, I have one value of x, which is Richard. So that knowledge base knows about John and Richard, and they could satisfy person x, right? Where John is x and Richard is x, right? Tell me about all of the persons that you know about. So this is referred to, the stream of answers is referred to as a substitution or a binding list. Now, this is available usually for systems, or for systems of knowledge bases that are made up of all horn clauses. So what's happening is you're getting variables that are bound to specific values. So again, tell me about all of the persons that you are aware of, right? So John was bound to X, Richard was bound to X. So we could get a series of answers, one after the other. And when you're playing with the queries in Prolog, you'll see this, okay? So let's see here. How about the kinship domain, right? So let's talk about family relationships. All right, so let's consider some simple facts. Right? Maybe Elizabeth is the mother of Charles, and Charles is the father of William, and one's grandmother is the mother of one's parent. Right? So your grandma is the mother of your parent. Okay, so some facts here. Right? So let's note some things. The objects in this domain are people, and we've got a couple of unary predicates. We've got male and we've got female. Now, kinship relations are going to be binary, right? Someone is the parent of someone else. Someone is the sibling of someone else. Someone is the brother of someone else. Someone is the sister of someone else, and so on, right? Now, we can use functions to represent mother and father, because each person is going to have precisely one mother and precisely one father. Now, remember when we talked about functions previously, we were talking about how you have functions that are, they're basically serving as a one-to-one mapping, right? You're going to have one input mapped to one output. And again, these aren't functions in terms of, programming, C++ functions, right? So these are functions in the context of the logic that we're studying that's trying to map one input to one output. That's why we had those leg functions, for example. So we could have a function that's going to, map, one father to one son, okay? One mother to one person. Okay, so we can consider these functions and predicates in terms of other symbols, right? So let's go back and revisit universal quantification and some of the stuff that we grabbed from propositional logic. So you could say, well, one's mother is one's female parent. So for all M and C, for everything in the domain, for all M's or C's, right? The mother of some child, some C, is equal to M. If and only if that M, that object that's being represented by M, is female, right? And M is the parent of that C, right? So everything in this domain, for all things in this domain, someone is the mother of C, right? And that equals M, if and only if M is female and is a parent. M is a parent of C, right? So one's father is one's male spouse. For all entities, right? We say we have an entity W and an entity H. Okay, for everything in that domain, H is the husband of some W if and only if H is male and H is the spouse of that W, right? So male and female are disjoint categories for all entities, for all objects within a domain. That object is male if and only if it's not female. Parent and child are inverse relations for all entities, PC, right? We can say that P is the parent of C if and only if C is the child of the parent. Okay? So a grandparent is a parent of one's parent for all entities within a domain. Consider, pick any two entities within that domain. One entity is the grandparent of the other if and only if there exists some entity where that G entity is the parent of that P entity and P is the parent of that child entity. The P entity is the parent of that child entity. Right? So these sentences here are forming what are known as axioms within that domain. So what these things are doing is they're giving us some factual information that can allow us to draw some conclusions, right? And axioms are kind of like fundamental facts, right? They're like baseline pieces of knowledge, right? They're the very minimum. They're the foundation, right? It's kind of like in geometry where you talk about, well, a point is a point and a line is a line. It's just axiomatic. It's just given. These are these things, and then you can build all these other shapes using those axioms. Okay, so we also have definitions. So we can define functions, predicates, in terms of other predicates. Okay, so this is similar to how you think about software packages, right? And you think about how you've got library functions, right? So if you pound include CMath, right, and you've got some built-in functions in there, or you pound include CC type and you have some built-in functions in there, and then in your program you write functions that use those, okay, that use those. So definitions can utilize axioms to give you more detailed information. Okay, so more on this in a bit here. Let's see here. So axioms are the very, 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 very base. Okay, so some sentences are theorems, and theorems, they get entailed by axioms, right? So a theorem is implied by axioms. So let's consider for all x and y, right? You're trying to state that there is a bidirectional relationship, right? If some entity x is the sibling of some other entity y, that's going to be true if and only if some sibling or some entity y is the sibling of x, right? So this is telling us, look, siblinghood is symmetric, goes both ways. And so this thing right here is a theorem. It's an example of a theorem, right? Why? Because it follows, right? Or we can conclude that it's symmetrical based off of the axioms, right, that are defining siblinghood. So this right here is one axiom. This right here is another axiom. So we can provide this whole sentence, which is a theorem built on these pre-existing axioms, right? So, these things should evaluate the true, right? A theorem should evaluate the true. Now, theorems themselves, turns out, not required for a knowledge base, okay? Because you can run through and use some of the proof techniques, some of the algorithms that we saw earlier on a knowledge base that is just composed of axioms, and you can get the right answer. But it's going to be slow, right? By including theorems which are based upon axioms in your knowledge base, you can speed things up in a similar way to the textbook gives this example about physicists, and they're trying to do some physics, and so they can rely on theorems that have already been generated without having to prove those theorems, right? You don't have to start from scratch to do useful work in physics. You don't have to go back to calculus and build up these theorems and show that those theorems are true, and then from there use the theorems to prove whatever it is that you're trying to prove. You can just go with the theorems, right? So it speeds things up quite a bit. Okay, not all axioms are definitions, right? So some are going to give you some general information about certain predicates, and there's not any way that you can complete them, right? So some things remain partially defined, okay, and they can still be useful. So, for example, you can have just some facts. So Jim is a male. Jim is the spouse of Lauren. Right? There's no obvious way to say for all X person of X, if and only if what, right? So you can still use that person predicate even though you don't have to have a full definition, okay? And having partial specifications or partial definitions can still be useful, which we'll see later on, okay? So for all X, if you're a person, that implies something, okay? Or for all X, something implies you're a person. That is allowable in first order logic, and it is useful from time to time. For now, we'll just make a note of it. Okay, so let's look at some examples of this in practice, right? So I'm going to take a look at one example, maybe both. We'll see how long it takes me to get through this example here, but talking about numbers, sets, and lists. So you can build up the theory of natural numbers using axioms, right? So what are natural numbers? They're non-negative numbers. So what do you need to be able to build this up in first order logic? You need to have a predicate that's going to be true for natural numbers, right? We'll call that nat num. And you need to have one constant symbol, 0, and we'll have one function symbol, s, right? And that stands for successor, as in a successor to 0 or a successor to some other number. So what are successors? Well, 6 is a successor to 5, right? 10 is the successor to 9, right? All right, so there are these things you don't have to know about, but they're Peano axioms. They define addition in natural numbers. So we can leverage those to further the discussion in the use of the first order logic, right? So natural numbers themselves have a recursive definition. So we can start off and we can assert, right, that 0 is a natural number, okay? 0 is a natural number. And so we can say, okay, well, for all numbers, right, for anything that's a number, for all n in this domain, for all objects n, if it's a natural number, that implies that there's going to be a successor number for that number, right? So we're saying that, and let's see here. For every object n, if n is a natural number, s of n is 1, 2, right? It's going to have a successor, and it's also going to be a natural number. So what are your natural numbers? Start off with 0, and then the successor to 0, and then the successor to the successor of 0, and then the successor to the successor to the successor of 0, and so on, right? So we've used first order logic here to define natural numbers. Now, we need some further constraints. Okay, so for example, you want to say, well, 0 is not its own successor. So for any number in the domain, for any object in the domain, 0 is not going to be equal to its successor number, right? And you're also going to say, for all objects in that domain, right, if the two numbers are not the same, then that implies that their successors won't be the same, right? So if I got, 10 and 11, what this sentence is saying is, Well, if you got 10 and 11, those are two separate numbers. Well, then their successors aren't going to be the same, which is true because you've got the successors are going to be 11 and 12. Or let me give you another example. What if I have the numbers 3 and 6, right? Well, since they're not the same, their successors are going to be different as well. So 4 and 7. Okay, so now we can define addition in terms of the successors, right? So what does this sentence say? Okay, for all objects within the domain, if it's a natural number, that implies that 0 added to that number is going to be that number. So here we see that prefix notation, which at this point you're probably a little used to with Lisp. Okay, so this is just saying, look, you can add any number to 0 and you're going to get that number back. Now what about this guy right here? All right, so for any two objects in the domain, if we have one of those objects is a natural number and another of those objects is a natural number, if both of those numbers or both those objects are natural numbers, then that implies that if you add the successor of the first number m and n, then you're going to end up with a successor which is the sum of both of those two natural numbers m and n. Okay, let's see here. What else am I going to say? All right, so yeah, I mean, prefix notation here, right? We saw that in Lisp. It might be uncomfortable to use prefix notation, so the textbook says, well, let's use some syntactic sugar, and we'll just go ahead, and even though in first order logic, you use this prefix notation because, look, this is a function. The plus represents a function where you're saying this gets added to this, right? It's consistent with what we saw, like the relationship spouse, Jim and Lauren, right? So by using the prefix notation with arithmetic symbols, it stays consistent. So, you're saying, well, we're doing addition. We're taking the successor, right, of m and adding that with n, okay? But textbook says, look, you might not be used to that, so syntactic sugar, we're just going to change the syntax a little bit, and we'll go ahead and let it mean the same thing. So we can write the successor of n as n plus 1, right? So that second axiom that we looked at could look something like this instead. So for any two objects within a domain, one of them is a natural number and the other is a natural number, then that implies that the first natural number plus 1 plus n is equal to m plus n plus 1, using that infix notation. So that looks a little bit easier to understand than the way we had written it previously. Okay, so this might be a little more clear. Okay, fine. Let's go with it as long as you can understand what's happening. Right. So now once you have addition, it's really easy within that theory of natural numbers, expressing it using first order logic. It's really easy to define multiplication in terms of addition, right? Because what's 7 times 4? 7 plus 7 plus 7 plus 7. Right? What about exponentiation? Well, what's that? What's 3 cubed? 3 times 3 times 3. Right? So, there's others you can do too. You can build it up. So the point is, the entire theory of these numbers, right, of these natural numbers, can be built up from what? One constant 0, right? One function, okay, which was the natural numbers, okay, a predicate, or excuse me, the natural numbers was the predicate, and then our function was s of n, and 4 axioms, right? So we put these together, okay. All right, should we go into sets too? No, I think I'll well, let me just highlight it. Okay, so you can do the same kind of thing with sets here, okay? And I'll let you go through it on your own just to speed this up a little bit. But essentially, you can go through and express set theory in a similar way. What are some definitions you need? You have the empty set, which is a constant. A set which is a unary predicate for which is true for all sets. What are some binary predicates? X is an element of S or is a member. So here you can see that they're using that syntactic sugar once again, so that way it's a little bit easier to follow along by using syntax that's more familiar with you, right? Or for you, or to you. So you can imagine that if this was written, using the syntax of first order logic, the element here, the element of symbol, which I can't highlight for some stupid reason, the E, that would be the name of the function, right? And then you can imagine that x comma s would be the arguments, okay? Anyway, so we can write it this way instead, fine. S1 is a subset of S2. Those are your binary predicates. Let's see here. So some possible axioms for you. Again, I'll let you go through and skim over that because I already gave you an example previously. But let me just give you one example here. So what does this say? An empty set cannot have anything added to it, right? So this is saying there does not exist a combination of objects x and s such that you can add x and s together to get an empty set, right? So think about your domain, all of the things within the domain. There are no two objects that you can combine together that's going to allow you to create an empty set. That's what that means. So some additional examples here. Two sets are equal if they're subsets of each other. So you can say here, all right, for all S1 and S2, S1 and S2 are equal if and only if S1 is a subset of S2 and S2 is a subset of S1. So I'm just going through and highlighting some of these examples here just to show you how you combine these sentences to get a definition of what it is that you're trying to describe, okay? Intersection for three objects here. Let's see here. So what do we got? For any three objects, x, s1, s2, x is going to be a subset of the intersection of s1 and s2 if and only if x is both an element of the s1 object and x is an element of the s2 object, right? So, for any three objects, the only way that x is in the intersection is if it's in the intersection and it's also in S1 and S2. It goes both ways, okay? And then this is an example of, how you could define a union of two sets, okay? All right, so we're almost done here. So lists themselves, going to be like Lisp here. It's going to look really familiar. Lists are like sets, but the thing is, lists can be ordered. Elements can be duplicated. What are some properties? Nil is the constant list with no elements in it. Remember cons, remember append, remember first. Okay, there's also rest. These are functions. Find, predicate for lists as member is for sets, as a predicate for lists as member is for set. What about list question mark? Right, so this is something that would evaluate to true only if you've given to it, something that is a list. Remember that is a list. So in Lisp, that takes the form of the list p function. Okay, so some examples here. Cons, x comma nil, that's a list with one element, right? Maybe you were playing around with that in Lisp, and so that's where that comes from. A list of many elements is A, B, C, right? And that's the product of, some of you answered this question on your test, writing it the exact same way, right? By putting together a bunch of nested cons ending with a nil, okay? All right, so let's tie this up by circling back to Wumpus World, okay? So the agent in Wumpus World had a list of percepts, 5 elements, right? There was, stench, breeze, glitter, etc., right? Now, we need to store those percepts along with time. Remember we talked about how time, because if you had similar lists of percepts, then the agent wouldn't know which one to go with, might get confused, right? So, you want to know, well, did I perceive the breeze on turn 1 or turn 2? Okay. If you just add breeze, then it's kind of ambiguous. So here's what a typical percept sentence could look like, right? So we're saying, all right, well, this is our percept. So what do we have? Here's what the agent perceives: stench, breeze, glitter. Nothing else on turn 5. Okay? So what we have is a binary predicate that has constants placed in the list, right? So stench, breeze, etc. So here are some possible actions that could be taken in response, defined in first order logic. Turn right, turn left, move forward, shoot, grab, climb. Okay, now we could ask the user, hey, what should we do? Okay, and remember the ask bars? Well, does there exist an action that is the best action on turn 5? Tell me what it is I should do. Now, the best action would be mapped to that variable A, and so the query would bind to that variable A, grab. So then your program or your agent function could return grab as what you should do. Right? Now, that percept data, the raw percept data, that allows you to draw some conclusions, to figure out some facts, and imply some facts about the state. That include, as some examples, right, for all TSGMC. Okay, so what is this, right? So these are all representing the possible objects. Okay, so for all of the objects, that could be S, that could be G, that could be M, that could be C, right? Representing all the different possible percepts in time. Okay, this is saying that for anything else, any other objects at any possible time, okay, whatever these are, doesn't matter. Okay, we've hard-coded in breeze. Okay, if we perceive a breeze, then that means that there's a breeze on turn t, or time t. Okay, so a similar thing for any objects in the domain. If we perceive, no matter what those objects are, if we perceive glitter, doesn't matter what time, that implies that there is glitter, that we have seen glitter on turn t, right? So what these are, these rules here, they're examples of a reasoning process called perception. Okay, called perception. Now, unfortunately, the textbook talks about that concept, that reasoning process in more detail, fleshes out in chapter 24. We're not going to get there. Semester's almost over. Okay, but these are an example of that reasoning process, and if you want more in-depth information on that, feel free to review chapter 24 on your own. Okay, so what about representing the environment of Wumpus world? Okay, well, here's an example. If you want to represent or have a rule that says, all right, well, this is what it means for squares to be adjacent. Okay, so these are ordered pairs, x, y, a, b. These represent the row number, column number. Okay, so for any set of these numbers, you're saying that the squares are adjacent if and only if x is equal to a and y is one more or one less than b, right? So they're adjacent only if x and a are the same, right? So you can imagine x is 1. Okay, well, if a is 1, then this part's satisfied. And you can imagine, well, what if y is 2 and b is 3? Well, then this part would be satisfied. Okay, so that's one example of them being adjacent, but they're adjacent if and only if that's true, or same thing for the x, right? If the second numbers are the same, okay, x or y and b are the same. If they're the same, so let's say they're both 2, okay, And the difference between x and a is at most 1. Okay, that means that they're going to be adjacent. Okay, so again, that keeps you from having to say, well, square 1 and 2 and square 1 and 3 are adjacent. Square 1 and 3, square 1 and 4 are adjacent. You don't have to repeat that over and over again, because you can use this universal quantification and this, this function notation in first order logic, along with the notation that we grabbed from, or that we brought in from propositional logic, to be able to succinctly state what it means for squares to be adjacent to each other. Now, we don't have to distinguish amongst the different pits, a pit's a pit's a pit's a pit's. So the unary predicate pit is sufficient. We need a binary predicate adjacent here because we're describing two squares, essentially, the coordinates of two different squares. Now just finish this off with a couple more little points here. So there's only one wumpus, so you can just have a constant wumpus. Now the agent location is changing over time. Okay, so you can say, well, at. So what is this? So this is saying that agent, the agent is at some square s at time t. Okay. Now, we want the wumpus's location to be fixed for all time, because remember the rules of the game, wumpus never moves. So for all time, the wumpus is at this square, right? So it doesn't matter what t is. So t could be turn 1, turn 2, turn 5, turn 27, turn 89. It doesn't matter. It's universally quantified. It doesn't matter what turn it is. Wumpus will be at square 2, 2. It's going to be at space 2, 2. Okay? And objects can only be in one location at a time. Okay, so here you've got, for all objects x, s1, s2, and t, what's this saying? Some object x can only be at some space 1 at a particular time, or if it is there, I should say, and that object x is at some square at times 2, that implies that space 1 and space 2 are the same. Alright, so this sentence is just saying, look, objects can only be at one location at a time. Right? So this is saying for any object x, space s1, any space s1, any space s2 at any particular time, if x is at space 1 for a particular time and x is at space 2 at a particular time, well, that implies that those spaces are the same, right? That's just a way of writing out saying you can only be in one location at any particular time. Let's see here. I think there's one last thing here. An agent can figure out, it can conclude, it can deduce, it can infer properties of the square using Percept. So if an agent in a square feels a breeze, then that square is going to be breezy. So how could we write that? Okay, so for any objects in the domain S and T, if an agent is at space S at a particular time and perceives a breeze at that particular time, that implies that it's breezy in that space. Okay. Let's see here. Pits can't be in breezy squares. Pits don't move, so we don't have to have any additional sentences for that. Let's see here. So how can we state that or deduce that which squares are breezy or smelly or not? We can discover which squares are breezy or smelly by letting the agent deduce where those pits and wumpuses are. So here's one axiom that can be used to describe that. So you can say, all right, for any space, right, a space is breezy if and only if there exists some R, right, that's adjacent to that space and that thing is a pit, right? That object R is a pit, okay? You can model time with successor state axioms for each predicate. So take a look at this right here. Let's see here. So this was from the propositional logic where we said have arrow t plus 1 if and only if you have an arrow at t and you didn't shoot at t. Well, instead we can write that using universal quantification in first order logic. So it looks like this. For all time, if you have an arrow at t plus 1, or if you have an arrow at t plus 1, you'll have that arrow at t plus 1 if and only if you have an arrow at t and you did not take the action to shoot at that time, right? So that might be a cleaner way of doing it. All right, so that's 8.3. So what did we talk about in 8.3? Basically went through and said, hey, let's talk about an interface to a knowledge base that would have to be implemented, the ability to tell the knowledge base, give the knowledge base knowledge, right? Put some stuff in your knowledge base, be able to ask your questions or ask your knowledge base questions in different ways. We looked at that. So it was tell, ask bars. Talked a little bit about axioms, definitions, theorems, and then went through some examples of using first order knowledge to build up the theory of natural numbers. And then I skimmed over quickly in the interest of time, pointed out some of the elements of how you could do a similar thing in set theory. And then we showed how we could apply first order logic for our Wumpus world, right? We didn't go through everything that you would need for Wumpus world, but just enough to give you a feel for how you could, talk about the environment, how you could talk about, where the agent's currently located at, and some of the other rules within the Wumpus world.